Here is the question that I ended the previous part of this lecture with. And what we need is to use our definition of the y component of average velocity, which is a rise over run. And so we're working from 0.1 second to 0.6 seconds, and so plugging that in, we have this, which gives 4 meters per second. Probably, again, the most common error would be to not do delta y over delta t, but instead to do y over t. So that would just be 3.1 meters over 0.6 seconds, and that gives you the incorrect value of 5.17 meters per second. Okay, now let's ask the similar but rather different question: what is the y component of velocity at time t4? So I'm asking about an instantaneous velocity. Now it's not obvious from the picture how we might determine that, because it looks like the velocity is changing constantly throughout this motion. Probably the easiest way to see how to answer this question is to look at the y versus t graph. So here's a blow-up of the y versus t graph, focusing in on some of the early data. And notice that the slope is changing now. Most of the motions we've looked at before have been straight line segments, but this one appears to have a changing slope. It's not very steep early, and it's much steeper later on. So in other words, the ball was going slow early and fast later. Well, we can interpret our average y component of velocity calculation by thinking of this slope. So our Vy49, which is our average velocity from t4 to t9, is the slope of that green line there. Now what we would really like is something that represents the slope at t4. Well, think about that. We could get the average velocity from 4 to 7. We could get the average velocity from 4 to 5. And if we had more data, if we had, for example, film at a higher frame rate, we could get even smaller values of delta t. What we're doing is we're taking a limit as delta t goes to 0. This may not be familiar to you because we're hitting on some calculus for the first time, but you can think of it for now just as meaning that we're looking at smaller and smaller time intervals and seeing what happens to these average velocities that we calculate as we look at smaller and smaller time intervals. Now we can imagine that there is a curve that goes through all our data. The ball, after all, was actually at various locations in between our data points. We just haven't been able to measure them. And so there should be a curve something like this. And what we're really looking for is the tangent line to that curve, that function, at t4. Now notice that those averages we've calculated, the 4.9 average, the 4.7 average, the 4.5 average, are getting closer and closer to that tangent line. So this limit, as we let delta t get smaller and smaller, is getting closer and closer to the actual slope we want, which is the tangent at t4. This is what we define as the derivative. You need to become proficient at just looking at graphs and making decisions about sizes of quantities from them, and so that's what this is about. So have a look at this graph that I've just been talking about and decide which is larger, the average y component of the velocity from t4 to t9, or the instantaneous y component of velocity at t4.